Hi. With this video, I want to talk a little bit about some statistical properties of this Monte Carlo estimator. Right, so we're going to estimate the probability of failure by counting how many failures we get out of n simulations. And there's some interesting insights we can get out of this in terms of the performance of this technique. So to set this up, we're going to do another change of variable. So I'm going to define a QI. QI is equal to the expected value of G of xj, or this is boldface x. So I'm going to sample an xj, and I'm just going to see, did I get a failure or not? And I'll call it qj, just to give me a little bit of shorthand here for some of these derivations on the next couple slides. So qj is a random variable, and I'm just going to draw samples of it. But those samples, qj is going to equal 1 if I get a failure, and that's going to happen with probability pf. So there's a pf chance that a sample is going to cause a failure, by definition, and it's going to equal 0 with probability 1 minus pf. So that's a 1 minus pf probability that I'll sample an xj to give me a non-failure. Okay, so the expected value of qj is 1 times the probability of getting a 1, pf, plus 0 times 1 minus pf, so that's equal to pf, right? So on average, I'm getting the pf out of this. And then for any one sample, I can compute a variance as well. This is the variance of a Bernoulli sample. This is a reference result, but we can rederive it. So it's the expected value of qi squared minus the mean value of qi, that quantity squared. So the expected value of qi squared, I'll take a 1 squared times the probability of getting a 1, pf, and a 0 squared times the probability of getting a safe outcome, 1 minus pf. And then the expected value of qi we got from the previous line, that was pf, and we just square that. Okay? So if we expand this all out, I've got a pf and a 0 and a minus pf squared. So I can rearrange that to a pf times 1 minus pf. Okay? So that's my variance. And then let's consider this Monte Carlo estimator, pf hat, which is the average of a bunch of samples. 1 over n sum I equals 1 to n of qi. So let's think about this one. So on average, the expected value of this thing is going to be the expected value of the way we're computing it, 1 over n sum I equals 1 to n of the qj's, or j equals 1 to n. Sorry, I used j on all these indices. So the 1 over n can come outside the expectation. The summation, we can break that apart and just compute the expected value of qj in here, and that expected value we have at the top of the slide is equal to pf. So we end up with 1 over n times n terms out of the summation j equals 1 to n times pf, and the 1 over n and the n cancel, so we end up with just pf. Okay? So the expected value of this estimator is pf, so that's what we call unbiased. Okay? So on average, I'm not underestimating or overestimating the probability of failure with this technique. But for any set of n samples that I generate, there might be a few extra failures or a few less failures than we would get on average. There's still some variance here in this estimator. So let's talk about the variance now for a few minutes. The variance of pf hat, okay, that's the variance of the formula we're using to compute it, 1 over n sum I equals 1 to n of qj. Okay. And a variance is an expectation operation. And remember, one reference formula, because it's an expected value of p hat f squared minus p hat f minus the mean quantity squared. There's a square in there. So a reference formula is that the variance of some constant times x is equal to the constant squared times the variance of x, whatever x is. So when I pull a constant outside of a variance, it gets squared. That'll be important in a second. So I've got a 1 over n here. When I pull that outside of the variance, I'm going to get a 1 over n squared, because the constant gets squared. And then let's just do this in a couple steps here. We'll leave the summation alone for the moment. So it's the variance of the sum, i j equals 1 to n, qj. Then that variance, it's a sum of a bunch of independent terms. And since they're independent, I can compute their variances separately and add them up. Okay? And the variance of each term in that summation is identical. So I end up with n times the variance of qj. It's just n of the same thing. And let's see, so I've got a 1 over n squared in the denominator and an n in the numerator. So I'm left with an n in the denominator. And then the variance of qj we had on the previous slide, that was pf times 1 minus pf. Okay. So we see this variance of this estimator, this pf I'm trying to get at, depends on the probability of failure in the numerator, and then it depends on 1 over n. So as n gets bigger, I'm generating more samples to make this estimate. The variance of my estimator gets smaller. And that's what we should expect, right? The more samples I generate, the more confident I am that my PF estimate is close to the true PF. All right, another way that's really nice to look at this is to look at the coefficient of variation of our estimator. So we'll call it Greek letter delta, P hat F, and that's just equal to the standard deviation of the estimator divided by the mean of the estimator. Right, so we want to know how big is the standard deviation relative to the mean value. And so this is useful because as PF gets small, I'm not so interested in the absolute value of my estimation error, but how uncertain am I relative to the mean or the true answer. So let's take a look at this. So the numerator is just the square root of the variance we computed in the previous line. So it's the square root of PF times 1 minus PF over n. And then the denominator, the mean value of this estimator, is just PF. So in the numerator, I've got a square root of PF, and in the denominator, I've got a PF. So I'm left with a square root of PF in the denominator. And I'll get 1 minus PF over NPF, whole thing in the square root. Okay? So there's a coefficient of variation. Tell me, how uncertain am I in this estimate relative to the mean value? So there's 3 interesting observations we can make here. So first of all, it decreases proportionally to square root of n. Right? So as square root of n gets bigger, this coefficient of variation gets smaller. Okay? And if I want to cut the coefficient of variation in half, I need to increase n by a factor of 4. Okay? The answer also depends on PF, and we'll look in the next slide at specifically how that happens. So safe systems with small PFs versus less safe systems with large PFs, this coefficient of variation is different, right? Because the PF is in there. We'll come back to that in just a second. Interestingly, it does not depend on the dimension of. Okay. So that's, for me to speculatively write that, you might be like, no duh, the dimension X never showed up in anything here. But this does happen in practical situations often. I've had this conversation many times with students or collaborators or things like that, where they say, okay, let's do some Monte Carlo simulation to study this problem. How many samples do we need to generate? And let's say maybe we're looking at some like uncertainty and collapse of a building, and we need to generate samples of the ground motion inputs to cause collapse of the building and earthquake. So we do some back of the envelope calculations or do some tests, and we say, okay, we need 200 samples, n equals 200 in order to get enough confidence in the result that we're looking at. And then maybe in the project they say, okay, now let's add in some uncertainty on the structural response parameter. So now it's both the ground motion input and some structural modeling parameters are uncertain. So we have more uncertain parameters, so we need more samples from a Monte Carlo simulation, right? And that's what this third bullet point says, is if we add in some extra sources of uncertainty into the problem, we've increased the dimension of X, the random variables, right? So now some modeling parameters are also included as random variables. The dimension of X is higher, and intuitively, people generally want to make more samples in their Monte Carlo simulation to say, I've got more uncertainties, I need more samples. That's actually not the case according to this formula. It could be the case that those random variables change the probability of failure because we're changing our model, and that could have some sort of impact. But just having more random variables doesn't mean we need more samples in. And this is actually pretty important. If I've got a problem with lots and lots of random variables, my form algorithm gets pretty cumbersome because I've got lots and lots of things to transform back and forth from X space to U space. With Monte Carlo simulation, I have more things I have to simulate, but that's not a terribly hard problem. And I don't need more samples when the random variables number gets bigger. So this is a solution strategy that's invariant to the number of random variables with regard to how much work we have to do, which is great because remember back from the introduction, one of our constraints or one of our problem characteristics is that we sometimes have a lot of random variables. And when that's the case, Monte Carlo gets more and more competitive as a strategy. So that's something interesting we can see out of this one. The second observation is PF. Let's talk about that a little bit more. And I've actually got a figure in the slides here. Here, what I did is I've rearranged the equation from the previous slide and solved for n. So now I squared both sides, multiplied both sides by n to get it over to the left side, divided both sides by delta squared to put it in the denominator. And then I've got this. So now we see that the number of samples I need depends on the probability of failure of the system and on my coefficient of variation of my estimator that I want. Okay? So here's a plot of that result in the bottom figure here, plotted for 3 different values of coefficient of variation. So coefficient of variation of 0.1, that means the standard deviation of my estimator is 10% of the true value. Right? And if we assume for a second, and it's not a bad assumption, that the errors are normally distributed, it says 2/3 of the time I'll be within plus or minus 1 standard deviation. So if a coefficient of variation is 0.1, that means 2/3 of the time my answer from my Monte Carlo simulations will be within 0.1 of the true answer, or within 10% of the true mean. Okay? Or I could have 2/3 of the time my estimate is within 5% of the true mean, or within 1% of the true mean. So that kind of controls the coefficient of variation. And then the other thing left is the probability of failure. So let's look at this. So I've got kind of probabilities of failure on the x-axis, and then the 3 lines showing the different coefficients of variation. And then the vertical axis here is the n from that top formula. So one thing we can see is that I've put this in kind of log scale, and then we end up with this linear result. Another way we can see what's going on here is that I've got these for getting to small probabilities of failure. We've talked about kind of 10 to the minus 1 to 10 to the minus 5 are probabilities of failure we're often interested in. As we get to small probabilities of failure, notice that numerator is 1 minus a very small number, and then the denominators, those numbers will vary in ways we see. But it turns out if probability of failure is small, this is pretty close to 1 over delta squared PF when PF is small, because then 1 minus PF is approximately equal to 1. So we can get rid of that numerator. And that's why these lines look straight in the bottom figure. So I've got these reciprocal relationships that n is proportional to 1 over delta squared. So that as delta varies, the pattern will change, but n is proportional to 1 over PF. So if I plot this log, a 1 over x line turns into a straight line. But okay, so that's what's going on here. So we've got this kind of linear increase in the number of samples, but in a log scale, with PF decreasing logarithmically. So I flipped the order of the axis here. And let's just read off a couple numbers, right? So if I've got a true probability of failure of 0.1, and I'm willing to tolerate 0.1 on my coefficient of variation, I need 10,000 samples. That's not too bad. But if I say the probability of failure is 10 to the minus 4, now I'm looking at 10 to the 6th samples, so 100,000 samples. Okay, that's getting bigger. I'm definitely not going to do that in Excel, but I could handle that in a computer program. But then what if I'm not satisfied with 0.1 for my coefficient of variation? What if I want this pretty precisely? If I was looking for a 0.01 coefficient of variation and I had a 10 to the minus 4 probability of failure, now I'm looking at something like almost 10 to the 8 simulations. This is like millions of simulations. And these number of simulations can get really large when we're looking at these situations where we have small probabilities of failure, which we often do, and if we're interested in reasonable precision in our answer. And that perhaps makes sense, right? We talked about that in the intro video, that if I've got a 10 to the minus 4 probability of failure, that means that only 1 in 1,000 of my samples on average is going to give me a failure, right? And so I certainly need a lot more than 1,000 simulations to even be confident that I'm going to get a probability of failure estimate with any sort of confidence. And it looks like I'm going to need like 10 or 100 times that many to get 10 or 100 failure observations, and that'll get me in the kind of 0.1 coefficient of variation range. If I really want a lot of precision, I'm going to need thousands of samples of failures out of all my samples. And to get like thousands failure samples out of a system that only fails 1 in 1,000 times, now I need 1,000,000 simulations already. And so you can see why the number of samples I need gets big in a hurry. And so that's a problem we're going to have to overcome if we want to use this strategy more broadly. And so the next video, we're going to talk about some tricks we can do to modify this kind of brute force Monte Carlo strategy to try to make it a little more efficient and not have to do quite so many simulations. But hopefully that's it for this crude Monte Carlo calculations. And hopefully you can see how we can use these expectation and variance calculations to get a handle on how many simulations we might need. And so this is a situation where even though we're doing kind of computer-based calculations, you can see just a few slides of back of the envelope calculations really gave us some intuition around how many samples we're going to need and helped us see, ooh, we're going to be in trouble here in some circumstances. Let's see if there's something clever we can do to get around that. Okay, so that's it for these kind of mean and variance calculations for these estimators.